Hello, in this video, we will analyze several well-known algorithms. First, let's look at the binary search. So this is the binary search. So we have this is size 20. And now to search if 24 is in this array. So now compare 24 with the middle element. 24 is less than 31. So now the search is now narrowed to the first part. If 24 is greater than this element here, and then the search will be in the second part. So every time you perform this one comparison, and you reduce the size of the remaining search by half, we can now use this function here, Tn, to represent the time for the search for the size of the array is in. So after you perform this one comparison and the time is reduced to 2, this n divided by 2, and then further divided by another 2. So then eventually you get to this n divided by 2's k. So for this k is log n, and this is T1, and here you see this is k. See here, k is log n. So eventually the time complexity is out of log n. So this is a very efficient time and the logarithm time. And the best is 2. 2 is ignored because it's a constant. It's a very efficient time. So if you double the size and you just increase the comparison by 1, if you square the input, and you only get 2 times more. So this is a super efficient logarithmic algorithm. Now let's look at the selection sort. So this is the selection sort. So let's put this 15 and reset the size here. Selection sort, you find the smallest element and swap it with first one. So this, and now the remaining list, you do the same thing. So you can now analyze this using this Tn is this, the first time is you perform the n-1 comparisons to find the minimum element. And then in the remaining one, so you are looking at this, finding the smallest element, and that's n-1 times further down. So eventually this is the only one time. Add all this together, and you're going to see this is out of n squared. Now let's look at the time complexity for the towers of a Hanoi problem. And the tower of Hanoi problem, we move the disks from the tower A to tower B with the assistance of tower C. And we do it recursively, move first the n-1 disks from A to C with the assistance of tower B, and then move disk n from A to B. And finally do it recursively, move n-1 disks from C to B with the assistance of tower A. So this is do it recursively, and we can now analyze it as this. Is this Tn, is the time complexity, is you do this Tn-1 time, so that is the first step here, move the first n-1 disks. And this is one time, it's corresponding to the step 2. And this is Tn-1 corresponds to this step 3. So you're going to reduce it, eventually you get all of 2's n. So that is called exponential time algorithm, because this is grows really, really fast. So this is, it's very expensive time. Now, when we do all this analysis, and so we use the common recurrence relations, this is all the common relations, recurrence relations we use is, this is for Tn, so you reduce it by half and with a constant time, and eventually that's a log n time. So like a binary search and Euclid's algorithm, which will be introduced in section 18.6. This Tn you reduce the t n minus 1 with a constant time, this gives you linear time. So those are the recurrence relations, and so we use very frequently, and so please take a look. Now let's compare all these common growth functions. It's a linear time, and this is the order of n. It's a constant time, order of 1, and this is the logarithmic time, that is order of log n. This is order of n log n. It's a log linear time. It's order of n squared, this quadratic time. And this is the n cube, it's cubic time. It's order of n to the n, that's exponential time. So look, this is the function. You can see that's the constant time. It doesn't matter how n increases, and the time is always order of 1. And this, it's order of log n, it grows really slow. And this is linear time, it grows with as n grows, and it grows proportional to the size of n. So this, all of this here, this is illustrated in this diagram. That is all for this section on analyzing algorithm time complexity for several well-known algorithms. See you on the next video.